In section 1 of chapter 9, we're going to be reviewing something that you've already gone over in middle school / algebra 1. It's something that we've even gone over in this class a little bit, but it plays such a pivotal role in this upcoming chapter that I wanted to make sure that, again, we cover it so that it doesn't surprise you and you know how to utilize a specific tool. The thing I'm talking about is compound functions. But first, I want to review some elementary mathematics, which is, let's say I define two functions, f and g, as the following. I say there's a function f of x, which can be written f of x is equal to 3x plus 1, and then there's a function g of x that is equal to x squared minus x plus 5. One of the benefits of function notation is it allows us largely to get over having to describe problems verbally in what I want you to do. What I mean by that is, if I wanted you to replace these x's with, say, a 2, I don't have to write that or type that. I can just say f of 2. And that is enough to tell you, I want you to plug 2 into the function f and tell me what its value is. So what you would do is, just like how in the function f of x, I replace this x with a 2, in the function f, I'm going to replace x with 2 and simplify. So 3 times 2 plus 1, which is equal to 6 plus 1, which is equal to 7. Yay, we are done. I could also do something like g of negative 4. And now that tells you I don't want you to take the negative 4 and plug it into the red function f. I specifically want it to be plugged into the blue function g. So it gives us a name, it tells us what we're going to input in as a value, and it tells us which function we're going to plug it into to begin with. So that would be equal to negative 4 quantity squared minus negative 4 plus 5. Take note, since function g had two x's, I had to plug negative 4 into the function twice because it needs to take up both spots. But then negative 4 quantity squared would be positive 16. Negative 4 is plus 4. And then we just add all those together and you'd get 25. Now this shouldn't be coming too much of a shocker, but what we're going to be doing today is a variant of this. We're going to be doing what are called composite functions. So what's a composite function? Well, a composite metal is a metal that is made up of two different metals. For example, bronze is made up of tin and copper. You take tin and copper over a certain mix and blend them together, you will get bronze. That's why we have the Bronze Age, was something that was a special marker in our timeline because we invented a new metal that had really, really great properties. A composite metal is two metals that are separate, blending together to make a new one. Composite functions is the same thing. We're going to have two functions that are distinctly different from each other, and we're going to blend them together, and we're going to utilize this function notation to do that. So what I have two functions, f and g. And what I am going to do is I'm going to find the composite of the function f and the function g. So what I could do is I could write it as the following. F of g of x. And what that is stating is I am going to take the function g and substitute it into the function f. I'm going to replace x in the function f with the entirety of g. So that would be equal to 3 times x squared minus x plus 5 plus 1. So I took the x value in the function f and I replaced all of it with the function g. I think it makes sense, since we're dealing with a red and blue function, that when I take the composite, they would be purple. That would give me 3x squared minus 3x plus 15 plus 1, which is equal to 3x squared minus 3x plus 16 as my final answer. Additionally, there is another type of notation that we can use. It is sometimes referred to as the FOG notation, F-O-G. Because typically when we math teachers introduce this notation to you, we'd introduce it with two functions f and g, and when you look at it, it'll spell the word fog, so it's colloquially called the fog notation. What I'm about to write is no different than this. I'm literally going to write the exact same problem, just with different notation. So I'm going to go through it the exact same way. So another way that I could write this is f, of g, and we typically put that in parentheses, of x. These two are the same thing. Again, I really want to reiterate that. They are the same thing. They mean the same thing. We're going to do the same thing. There is no difference in their processes. So it will be equal to, I'm going to take the function g and plug it into the function f. So it is again going to be 3 times the quantity of x squared minus x plus 5, quantity plus 1, which is then going to be equal to, distribute the 3, and then combine the like terms, which are the constants at the very end, and that would be my answer. The one thing I also want to get across is that f of g of x is not the same thing as g of f of x. If you swap the order of the functions, you get something entirely different. So for example, here's my second example, is if I get g of, g of f of x, I am going to take the function f and plug it into the function g, and I'm going to get an entirely different value. Now the function g has two x spots, so I actually have to plug the 3x plus 1 into this function twice. So this is going to be equal to 3x plus 1 squared minus 3x plus 1 plus 5. Here's the biggest mistake I see students make when they do this process. When I ask you to take 3x plus 1 and square it, a lot of students just distribute the second power and go, oh, it's 9x squared plus 1. That is incorrect. The way that you should visualize this is 3x plus 1 times 3x plus 1. You're going to have to FOIL that. That negative is going to be distributed to the 3x and the positive 1, leaving me with negative 3x minus 1. Now let's FOIL that binomial. We have a binomial times a binomial. It'll be the first term times the first term. 3x times 3x is 9x squared. 3x times the second term of 1 is going to be plus 3x. Then we take the second term and multiply it by the first term. 1 times 3x is 3x. And then last we take the second term and multiply it by the second term. 1 times 1 is 1. And minus 3x minus 1 plus 5. So again, note, you don't distribute the second power because 3x plus 1 quantity squared is going to actually turn into 9x squared plus 3x plus 3x plus 1. There are 4 parts to it, not 2. Last step, combine the like terms. You'll have 9x squared plus 3x plus 5. And that is our final solution. And notice it is completely different than the other notation. It's completely different than the other composite function because the order was different. If the order is different, you will get a different function.